Hi, I'm Josh. I'm an NLP engineer here at Titan, and I'm going to be walking you through how to do structure generation using language models. So why might we want to do structure generation? Why do we want structured data as an output rather than unstructured data? Well, the main reason is it's just a lot easier to work with in downstream tasks. So adhering to a schema means that you know what the format of the data is going to be, which means that for tasks like document extraction or retrieval augmented generation, the data can be put into, say, database or some structure you're using for onward processing. And part of this is that you get guaranteed consistency among your data types. If you know that you need to output a float, then having a guarantee that you're going to get a float makes it a lot easier to build later parts of the pipeline that rely on that. So what does this mean in practice? Well, I've got some example generations for the question of when was Bob Marley born, and there's sort of 3 different versions you can get here. If you just prompt an LLM to say when was Bob Marley born, a lot of the time you'll get this sort of unstructured format. Bob Marley was born on 6th of February 1945 in Nine Mile, Jamaica. And this is useful if you're having, say, a conversational chatbot with someone, but it quickly becomes a bit cumbersome to use. If you want to fill in, say, a database downstream, at least for this example, you have to do some post-processing, and it's not overly complicated post-processing, but it can quickly get out of hand. So for example, if the LLM decided to output the def date as well, you'd have to figure out which date to use. Or say it decided to switch up the format and you'd only use some simple parsing of statements to be able to gather information out. So the second version is the semi-structured one, so 6th of Feb 1945, and this is more useful and you can get it with some good prompt engineering, but it's still not ideal for downstream tasks. There's no guarantee that the date format is going to be kept the same, and there's just no standard scheme generally. Whereas the third version, this is in a structured form. So here's the ISO 8601. It's basically just a year-mm-dd format. And this is easily ready for downstream consumption. You can put it straight into a database, and you know that your answer is always going to adhere to this schema. So how could we specify this sort of form? How can we describe it? So regular expressions is specify formats that strings should match. For example, you could describe floats as roughly as digits with a decimal point somewhere and then a plus or a minus at the start. So for that pattern we had before, that's what the regex would look like. It's quite horrifying, but it's basically saying we want any 4 digits and then a dash, and then any of 01 or 02, etc., or any of 10, 11, 12, so that's for the months, and then another dash, and then a similar thing but just for the date ranges. So only allow 30 or 31 if it's going to be starting with a 3. So regular expressions are equivalent to something called finite state machines. So these are sort of the best way to think of it is little robots that have states and transitions, and you start in this start state, and whenever you see the thing that's labeled on the arrow, you can make a transition to the next state. So for this pattern we had before, you start in this start state, and when you get a digit you go into the first one, and another digit you go into the second state, another digit the third state, another digit the fourth state. And this is saying we want 4 digits in a row. This double circled one, this is the convention for a final state. So if once we're in this state, then we can say, oh, the string that we've made so far, that's acceptable. So for this one, we want 4 digits, then a dash. Then if we're going to have a 0, that means that the day is going to be either 01, 02, 03, 04, whatever. So any digit that's more than 0, basically. Or if we go for 1, then it can only be the 10th or the 11th or the 12th month. Then we get another dash, and then we do the same thing again but for the days until we end up in this final state. So how can we do this with a language model? So at least for causal language models, they generate 1 token at a time. So each step we decide what tokens are going to be allowed next based on the tokens that have come before. So in this case, you can see here that when we have this dash, when we're in state 8, the only token that can come next is a dash. So say that we have this is our set of next tokens it could be, and these are their scores. This is basically just logits. Once we apply something called logic warping, we go from the 0 being the one that was going to be picked to all of these having a score of minus infinity, meaning that this is now the token that's going to be picked. It's got the highest score. This is called logic warping. We downweigh the tokens that are less preferable according to some function, but really here we're kind of actually doing logic masking. We're masking out all of the tokens that aren't valid tokens to generate at this step. Here we can only have a dash when we're in stage 8. And so we must get everything that's not a dash. But there is a caveat here. Regular expressions and finite state machines, they transition by character, but LLMs usually go by tokens, which tend not to be the same as characters. Given that most models will be using subword tokenization, you can end up with situations where the word fisherman is 2 tokens using, say, Llama's tokenizer, but it's actually 9 characters long. So this previous example, it worked well because every symbol in the alphabet of the FSM mapped to a single token of a tokenizer. So 0, the digit 0 is one symbol in the alphabet, but it's also its own token of a tokenizer. But in reality, what we end up having is that one subword token ends up consuming multiple FSM transitions. So to see what this looks like, say we have this sort of toy example, on the left is our tokenizer and the tokens that we'd be allowed. So we've got fish, ing, man, fisher, and then all of the letters are in fisherman, plus the G for ing. And if we look at this, there are multiple ways that we could step through this using multiple sets of tokens that could be generated to get valid sequences. So we could have fish, and then end up in state 4, then get an E, then get an R, and then get man, and then we get into S9, and we've outputted string fisherman. We could also just go F, then I, then S, then H, then E, then R, then M, then N, and N. We get to S9 and do the same thing to get fishing. We could also do fisher and end up in S6, and then take man. So this tokenizer, what's happening with something like fisher is we're consuming one token, but we're making multiple transitions in the FSM. So what you end up doing is you build up sort of mapping that for each state, what token can we accept, and then what state do you end up in. So at the start state, we can take fisher and end up in state S6. So in this tokenizer does happen to have a token for each individual letter, but that isn't guaranteed. And even if the tokenizer does have that, if it's been trained using a subword tokenizer, then it probably won't have been trained to output words letter by letter. So the result you're going to get from excluding these subword tokens by only allowing single character transitions, you're going to get some subpar performance. It's not used to outputting fisherman by generating F, then I, then S, then H, then E, then R. It's going to do it by fisher and then man. So you use some cool optimizations here as well with prefix trees to get this character to subword token mapping done quickly. You can kind of see how this could be turned into a prefix tree. So to kind of summarize that, you need to walk the FSM to determine what the valid token will be from each state. So for example, at state 4, ing, I, and E are going to be only possible next tokens, the I, the E, or the ing. There's no token for ermine. So it's an example of trying out some regex, and this is without using a. And this is when we have the regex string, what we get to value apply instead. You can see it actually adheres to the format this time rather than giving some slightly unhelpful LaTeX code. So having regex driven structuring is useful. The use cases for it are typically forming a certain data type or choosing one from a set of options. And there are some commonly used structured data formats, they'll abstract this away, and JSON is a common one for this. Plus JSON is also kind of quite a natural output format for a task like RAG. If you have JSON and you want to say that it has to adhere to a specific scheme, you can use something called JSON schema. So for this JSON on the left, it's saying that we're going to have an object whose title is person, where this is actually metadata, but the main thing is the properties here are it has to have a name and an age. And age has to be a number between 18 and 64, and the name has to be a string. And you can see that this JSON on the right has name as a string, age between 18 and 64, so this is valid JSON according to this schema. This is really useful for if you want to prompt a model, kind of any system, to say I need to have this structure as an output. So let's do an example of doing some RAG, but without using a schema, and let's see what happens. So you can see we're trying to get information about the city of Zagreb in Croatia, without using a schema, just prompting it to get required information. then it'll make some guesses about what we want, but there's no real easy way to specify what it was that we wanted. So how can we get this data in a structured way? Well, we could make multiple calls using regular expressions or prompt engineering and hope that we get a consistent format. So that could be something like saying, what is the capital of Croatia? That's one prompt. What is Zagreb's population? That's another prompt. Each time having to copy in the context. But we could also try and use something like guidance to do slot filling. So that's a package which basically just sends the information you want and some form of structure and says, all right, fill in this gap. But there is a problem here. It's very slow and expensive. You've got to do a lot of calls, and for big JSONs it quickly gets unwieldy. And I mean, I have personal experience of this just taking a very long time. So you think, all right, what's a maybe smarter way we can approach this? You think, could we write, using what we've seen so far, could we write the JSON schema that we need as a regex? Well, yes, but it's very complicated, in that they also become very kind of difficult to create or modify. You lose a lot of the flexibility you get from generating JSON as well. So, for example, a certain key, you're going to have to generate that first, even if the model isn't ready to do it yet, just because of the way that the regular expression has set it out. So, is there a better way? Well, much as an FSM can represent a regex by showing what characters are allowed at each stage, an FSM can also represent a JSON schema by composing the primitives that you're allowed together. And the Pydantic package is a good way to compose these JSON schemas in Python and to sort of represent them. So for this previous Zagreb example, say the data we might want out is this schema at the bottom here. So we want to know what country it is, how far above sea level, what the districts of the city are, what the population is, its dimensions, like its size, and say its mayor, or who the first mayor was in this case. So you can see that Pydantic you can compose objects together here. We have this country object which only has one field string, but you can add other things to that if you want to have more information about Croatia. Say you have a description of its flag in the text body or somewhere. And it also uses sort of standard primitive types. So the distance above sea level we know is going to be an integer. You know the city districts is going to be a list of strings. And Pydantic has an inbuilt method that allows you to convert this very handy scheme into JSON schema. So this is JSON schema on the right. You can see it sort of resembles one we looked at before. So you can see that JSON schemas can be used as FSMs. FSMs capture rules, and these rules can define types, but you can also compose these FSMs together. So on the left here, we've got an FSM for an integer. So you can see that we start in state A0. If we get a plus or a minus, which is allowed before an integer, then we end up in a non-accepting state where we have to get a digit, because plus or minus, they aren't integers. It has to be +1 or -1 or something. But we can also just go straight with a 1, being in an accepting state. If we say got +1, then we end up in A2, and we want to make say +11, well that's fine, we just add more digits on, and we can keep doing that forever. So this can be composed together. If we want a list of integers, well then we start in S0, and we have to get an open bracket to start our list, and we might have an empty list. We might just go straight for a closing bracket, being in an accepting state. But more likely, we end up in a state A0, where we can then finish the integers FSM. We then end up in this state AT, the accepting one, which corresponds to down here, and we can then either have a close bracket and our list, or we can have a comma, which puts us in another state, where we're then welcome to go back and generate more integers. However, doing objects like dictionaries this way is trickier. The main question here is, should we enforce an order on the keys? If you look at outlines and JSON former, which both work with something like this, then they say yes. However, the finite state machine might want to output country before mayor, especially if the prompt didn't specify an order. And if we force the model to output the country first, then it could counteract some of the learned behavior and reduce the accuracy. Finite state machines also can't keep track of what keys have been fulfilled, other than by forming a new branch for every possible combination of keys that are fulfilled at a given time. So that you have to create a new branch for, we've done the country, so we now could do distance above sea level, city district population dimensions mayor, and then you end up with another branch for when you end up with, say, we've done mayor dimensions of population, now there are 3 more branches for what we could generate next. There's a technicality here that this is involved using an NFA. It's sort of beyond the scope of this video, but there's an interesting note here. Okay, so let's look at if we can input a JSON schema using what we've done to improve the RAG performance here. So just for comparison's sake, there was the previous version, and here again, we'll paste in our JSON schema. And this is the output. So total population, we get the example districts, the dimensions, the meters above sea level, the country, and who the first mayor was. And you can see this follows the format you want, the data types you're adhered to. So let's try it in a non-RAG setting. So here we just ask for a biography of David Cameron. If we're not using JSON schema, you can see it gives us a nice text bill, which is great if you're just wanting to chat or you're just reading it. It's not very useful for downstream tasks. So let's try this again, but we'll use a JSON schema this time. And you can see that the information that we need is coming out in a nice structured format, ready for further use. A kind of interesting thing to note here is that when we're using these JSON schemas, we can specify quite close to the actual generation of what the information is that we want. So the model can see that we want country. That will be the token that precedes what's being generated. And by specifying the schema, it's sort of like extra information can be smuggled into the generation process. And it's smuggled in with immediate locality to the point where we're trying to generate. So all this has been combined into what we call JSON Derulo, which are decoding rules for language outputs. So this is our solution for extracting or generating information into JSON following a specified schema. It has guaranteed adherence to the required types, and it lets you do this extra prompting within the keys. So tokens which detail specifics of the required information are immediately local to those which are going to be generated. And we're currently working on the ability to extract data solely as spans from an input text. So at the minute, RAG will generate using context, but there's no guarantee that it will take information directly from the text. And this can be especially important if you're, say, trying to get phone numbers out or something. Most of the time, they'll be extracted correctly, but you want to guarantee that it's not pulled some number from, it's not hallucinated an extra digit in. So, thanks for listening, and if you have any questions, feel free to get in contact. JSON Derulo is available now in Takeoff Pro, but we're happy to discuss any other structured inference applications you might have.